Hello and welcome to Science Solutions. We have an exploratory program for everybody today. It's about exploring the smallest and biggest mysteries of science. And we're joined today in this program by Professor Harvey B. Newman of the California Institute of Technology. And Professor Newman is an expert in experimental high-energy physics, computer science, experimental computing and software for high-energy physics, international data communications networks, particle accelerators, Large Hadron Collider at CERN in Geneva, Switzerland, and all of this in addition to his duties at the California Institute of Technology. So that's an awful lot. Harvey, welcome to the show.
I'm glad to be here.
Maybe you could explain to our audience the significance of high-energy physics. I happen to think that it's one of the most exciting areas of scientific discovery in basic science. To me, it's the great mystery of trying to figure out what our universe is made of. And it seems to start with small things rather than big things.
When we go to higher and higher energy, we also go to smaller and smaller distances. It's like a microscope. With the new microscopes, you could probe to see smaller and smaller things, smaller and smaller pieces of matter. Here at these highest energies, we can probe to the shortest distances. So we can resolve things, and we can also create new things that haven't been created before, at least not by mankind. And by doing this, by looking at what we create, how often we create it, the configuration of what comes out, how the particles are distributed in space, we can learn whether our present understanding of the fundamental forces of nature is complete or incomplete.
Now, in this program, actually, we're going to end up, one of the things we're aiming for in this program is to explain the relevance of subatomic particle physics to us right here in Monrovia. What does this mean to us? And we want to look at it in terms of both basic science, just knowledge, pure knowledge, and why is that important? And then we want to look at some applied aspects of what particle physics does, and look at both of these things and hopefully explain to our viewers why this program, we think, is very, very important. So maybe you could make a comment and then start showing us some displays.
Well, so this is a very good perspective because high-energy physics, the fundamental science, is the science at the high-energy frontier, a major frontier in which we get to learn what are the most basic constituents of matter and what are the forces of nature really. And also, when we go to higher and higher energy, there's a relationship to very high temperature. Why is that relevant? Because as we go backward in time towards the early universe, the universe was at a very high temperature, especially shortly after the Big Bang. So what we can do in principle is, with a high enough energy, create particles which haven't been seen in nature since shortly after the Big Bang. And that's one of our hopes, to create new types of particles, new interactions that we haven't seen before, to help to complete our picture of nature. And also, this is the kind of activity which has been shown historically to shape the nature of our civilization and the way we live. That's, of course, a very long view. If I think about analogies, you think about the experiments of Maxwell and Faraday, understanding electromagnetism. Without understanding electromagnetism, there'd be no electronics, no computers, no modern-day appliances, nothing about our modern life.
And all this began with just basic science, with curiosity, to find out how things worked.
To understand how things work and to gain new insight.
Now, one thing I also want to point out, I think we could ask a lot of people in the general public, how many physical forces do you think there are in nature? And I've had answers from people that, oh gosh, billions, at least millions. Harvey, how many physical forces are there that we have discovered in nature?
There are 4 fundamental forces. The strong force that holds nuclei together. The most prevalent one is electromagnetism. So all of chemistry, for example, is a result of the electromagnetic interaction. There's the weak interaction. The weak interaction is not so familiar, but it does govern things that we know about, like radioactivity. And then finally there's gravity. And gravity is very interesting. It's the one, of course, that people in our civilization have understood exists for the longest, but it's the one perhaps that we understand the least about. And part of the reason is, relative to the others, it's so weak, and only celestial bodies and very large accumulations of mass can have strong forces under gravity.
Okay. Well, with those explanations, maybe you can start with your displays and show us something about the basic science of particle physics and then also applied science. We're tackling something that's really a major issue and can scare a lot of our viewers. Oh my goodness, you're going to talk about the smallest and biggest things, and you are an expert in particle physics especially. And we're going to talk about these tiny little things that we don't even see, but that you have and your profession has determined are really there, or very highly likely there. And so I'm going to ask you a few definitions at first for our viewers that you can explain what we're talking about. First of all, the Large Hadron Collider, as it's called, is located at CERN near Geneva, Switzerland. It's a 27-kilometer or 17-mile around tunnel that's buried underneath the ground. I think you said it's how many meters below?
From 50 to 175 meters below the ground. Mm-hmm. It's actually tilted so that it fits between the nearby mountains, which are called the Jura Mountains, and the Geneva Airport.
And that sits all underneath there, and it really kind of, does it span over to the French border from Switzerland?
Yes, it spans the French and Swiss border. It's mostly in France, but the main part of the laboratory is in Switzerland.
And who funded this huge 17-mile accelerator tunnel? Who funded that?
Well, the CERN laboratory is a true international organization, which has now about 20 members, but also many other nations participate.
So it's funded by governments then?
Yes.
Okay. Is the United States a participant in the funding of the CERN network?
Yes, we are. We're a so-called observer state in the CERN scheme, and we contribute to the project, but not to the operation of the laboratory or to the building of the accelerator.
Oh my. So percentage-wise, what would you say the United States contributes out of the total funding?
Well, if I integrate over the years, just a few percent of the budget for operating the laboratory and the accelerator.
So a few percent by the United States. And
yes.
Which country, just out of curiosity, is the biggest contributor?
Well, there's a scheme by which, if you're a member, you contribute according to your gross domestic product. And one that's reached the maximum is Germany. It's about 20% of the budget.
Oh my. And so if we were to contribute, we would be
We'd
huge.
reach the maximum.
We'd reach the maximum, right, with our
Yes.
GDP.
Yes.
All right, well, let me ask you a couple of definitions here. This is called the Large Hadron Collider at CERN. What is a hadron?
A hadron is a particle which is made up of quarks, which are the fundamental constituents of matter, that feels the strong interaction. That's the interaction, the force of nature that holds nuclei together, for example. And so hadrons, the most commonly known hadrons are protons and neutrons, which are parts of the nucleus. As you continue to increase their energy, they acquire energy and momentum, but they don't get much faster. They just approach the speed of light to a greater and greater approximation.
So you get more momentum with
More
a bigger
momentum
ring,
and
right?
more energy.
And more energy.
So if you collide such high energy particles together, you can create new things. You can create additional particles. We collide protons together. What we're really colliding are the pieces inside the protons, the quarks, and there are additional particles called gluons, which had something to do with discovering, which bind the quarks together.
All right. And they're going to go head on toward each other until they finally crash into each other. So I see here you've got some questions on the nature of matter. What are the constituents of matter and the forces at the most basic level? on the origins and composition of the universe.
And its evolution. You know, can we describe with the physics that we know the early universe? We already know that we cannot, also the present universe. So what has arisen in the last decade is the knowledge that most of the matter in our observable universe is not the familiar matter. Compared to the normal matter that we know, there's 6 times as much dark matter, which at best only interacts weakly and governs, for example, the rotation of galaxies, and also dark energy, which is governing how far galaxies, particularly the ones where we're seeing the light from the earliest moment of the universe, why they're receding from us at an accelerating rate. Okay, so also you heard that in the standard model there are missing parts. One thing is something discovered by the mathematician Peter Higgs. So it's naturally called the Higgs particle, which is yet to be seen. It's a mechanism which would allow us to explain how particles gain mass.
That's called the Higgs boson, right?
Higgs boson.
And a boson is a particle that will carry the force, such as a photon will carry electromagnetism.
Right.
A graviton theoretically carries gravity.
Right. There are 4 carriers of the 4, well, there are 4 sets of carriers. The photon carries electromagnetism. There are 2 particles called the W and Z that carry the weak interaction, which have been produced.
So the LHC is attempting, through the energy that it has, which is, I understand is something upwards of 10 trillion electron volts, something like that.
At the moment, 7 trillion electron volts.
7 trillion electron volts, and trying to get more, I guess.
Yes.
And is this going to be enough to find out if this mysterious Higgs boson that supposedly is responsible for transmitting matter, is that going to find out?
Yes, actually, this is a very exciting time. Mm-hmm. We will have enough reach, almost certainly, in the next 2 years. We start running again on February 21st, less than a month from now. We'll almost certainly run for 2 years. And during this time, we'll acquire about 100 times more data than we acquired in the past year. And in doing so, we'll have enough reach to see if the Higgs particles are there or not. If it's not there, there'll be an alternative way that we can generate mass, for example. And the leading way is called supersymmetry. It's an extension of what we understand. What we understand we call the standard model that embodies what we know.
That's called the standard model of particle physics.
Particle physics. So our knowledge of the electromagnetic strong and weak interaction especially is encapsulated. And also the known families of quarks and leptons is encapsulated in the standard model. Supersymmetry is an extension of the standard model that solves a number of problems. First, if you project it back to the early universe, it is consistent. The 3 forces do come together. And so that means that the early universe could have been unified, that what we see is essentially different aspects of one fundamental force. It contains particles which could be what the dark matter is. So it contains candidates for the dark matter.
So would the fundamental force, if it exists, if we know of 4 physical forces, would this fundamental unifying force be a 5th force, or would it be just a combination of
It's a combination. Imagine in the early universe we had one unified force. At a high enough energy scale, it all appears as one force. As you go to lower scales, as the universe cools, there's a separation out of certain parts, certain types of particles. The first thing actually to decouple from the others would be gravity, if it is carried by gravitons. And then finally we end up with 4 forces.
Okay. Let's see what other questions are addressed here.
Well, why is gravity so weak? And there's no particular reason for that. And some people think now it's because there are extra dimensions of space. And people who are studying string theory found that there are, if you had extra dimensions of space, you'd get a much better behaved, much more consistent theory, and started to think about the consequence of that. And so now there are ideas that we, in our world with our 3 forces of the strong electromagnetic and weak interaction, live in a subspace of a larger space. And maybe gravity lives a short distance away, a very short distance away, but in a different subspace. And the two communicate only weakly. And that's what we see. We only see the residual effect of the basic gravitational force. So that's one idea that's arisen.
Would that suggest that it's harder for, let's say, gravitons to get through from that other aspect of space to our part of space?
Yeah.
Therefore, it's kind of a resistance that's...
So the analogy is molecules. So you have electromagnetic forces that bind atoms together, and you form molecules. And sometimes in many molecules, the binding between them is weak because the positive and negative charges are already together in the atoms, and only the residual effects between them remain. So you get these forces which have a very short range, and the force becomes very weak as soon as the two atoms are a short distance away from each other.
Right. I meant to say it makes the force weaker coming from one type of space to the other.
The force gets diluted. That imagine there are force lines, and in 3 spatial dimensions they spread out. So imagine you had more dimensions, then they would spread out more, and the density of the lines would be effectively weaker.
How many possible dimensions are you considering at this point in time?
A lot of these developments come from string theory. So they discovered that you could get rid of some of the theoretical problems we have associated with mathematical infinities if you had a total of 10 dimensions, 10 spatial dimensions.
Plus time?
Plus time. Then there's a more general theory that has one extra dimension called M theory that a lot of string theorists are focusing on. And that could be a picture in 11 spatial dimensions and time that encompasses all of the theories that we know about.
Okay, let's see some more here of what you've got.
Okay, why is any matter left in the universe? What that means is, why do we see predominance of matter over antimatter? There's no fundamental symmetry about particles and antiparticles that favors one over the other, except perhaps a small asymmetry, which is part of nature that we're trying to understand, which we haven't found the source of yet. What happened was, early in the universe, there was a tremendous amount, almost equal amount, of matter and antimatter. And then at a certain moment, like 10 to the minus 10 seconds, 1/10,000,000th of a second after the Big Bang, there was this great annihilation of all this matter and antimatter. And what we see is just a tiny residual left over. And we don't know why the residual matter even exists. So why is there any matter left in the universe?
So in other words, we're lucky, in a way.
In a way. Well, this asymmetry, which is a small asymmetry, is in a way responsible for our existence.
Okay.
What is the dark energy? I think this is one of the most important questions, and here particle physicists have no clue. It's something which has arisen in the past very few years, and we'd like to get a handle on it. And there are alternative ideas. Either there are particles and fields that create the dark energy or not, or maybe it has to do with the very fabric of space-time, and we just don't know. It's too new a set of ideas, and we're just beginning to even approach how to understand it.
Now, dark energy is believed, my understanding is that dark energy is believed to be either pushing or pulling the universe more and more open between galaxies at an accelerating rate.
Yeah.
They think that this acceleration, apparently, or you think it's due to dark energy. Is it pushing it or pulling it?
Viewed from here, it's pushing it. I mean, it's causing the edge of the universe to expand outward.
So here we are talking about tiny little particles we can't even imagine in our vision of seeing these little things, and yet they are so important that they're having a huge cosmological effect, which is why we're saying on this show we're exploring the smallest to biggest mysteries of science. Your field of science and inquiry is really dealing with the smallest and the biggest ultimately.
Yes, so what our universe contains also on a large scale, is dominated by the existence of particles and fields, even the vacuum. The vacuum is not empty. Some of the time the vacuum lives as fluctuations of particles and antiparticles. So a particle and an antiparticle pair is created, and then they annihilate in a very short time. And so the very nature of space-time is bound up with these particles and fields.
I see. Can we see the next slide?
Go ahead. So this is about the Large Hadron Collider. As Zane introduced, it's a 17-mile tunnel. This is just sketched on the topography of Switzerland and France. You see the Lake Geneva, and you see the laboratory in the foreground, and over here on the right you see the Geneva airport. And then on the left, the mountains are rising, called the Jura Mountains, and the ring fits in between and is tilted to fit so that it didn't have to tunnel too deep under the ground. If you go too deep under the ground, you enter layers of granite, and it was discovered in the civil engineering probes of the ring that sometimes that granite, which has cracks in it, contains high pressure water.
Oh, uh-oh.
And so originally it's 27 kilometers or 17 miles. Originally it was going to be more than 30 kilometers. And part of the reason it's somewhat smaller is to stay away from those hard to excavate and dangerous for completion of the project layers of granite beneath the mountains.
Okay, let's see some more.
Well, what it says at the bottom is that there are many things that we can look for. The Higgs was already mentioned. Supersymmetry, maybe more fundamental constituents of matter. Maybe when we reach a certain energy scale, we'll start to see new interactions which are signs of the fundamental gravitational force, not the weak one that we experience in every day. There are other things. For example, 1 month a year it runs where it collides lead ions and not protons. And that way we create new states of matter, so-called quark-gluon plasma, and we are able to look at the bulk properties of matter, but at extremely high temperature in the midst of nuclei, when the nuclei come together. So we do all that, and as experimentalists, what we want most to happen is that something will happen as we enter a new energy range, which is something that hasn't even been described before. I mean, we don't know what we will see, but we try to cover all the bases and also keep our minds open to new things happening.
Okay.
There are also technological challenges, which I'm also involved in. In order to build the experiment, to acquire and analyze the data, it's taken physics groups from throughout the world. So like it says here, in the program there are 8,000 engineers and scientists from about 400 institutions. 1,700 of them are from the US. The US is the largest national group, even though we're not a member of CERN. Mm-hmm. And then how are you going to analyze the data, and how are you going to involve all of these groups, including groups with young scientists at universities throughout the world? And so this is a scheme that I invented about 11 years ago, a so-called data grid system for this work, where thousands of terabytes of data are spread throughout the world over long-distance networks and analyzed cooperatively by groups everywhere in the world.
Now, another thing we should probably point out to our viewers is CERN is responsible for the creation of the World Wide Web. That was a practical applied idea that came from, of all places, a subatomic particle accelerating laboratory.
Yeah, well, it came from a summer project of Tim Berners-Lee, who just wanted to figure out how to share documents with his colleagues. And
all
so
over the world.
he invented a protocol and a way to do this. And you know, after kind of being tried out locally, it sort of spread, as everybody knows. Okay, so I thought I would just show a little bit in time lapse about our experiment, where you can see some of the instrumentation. This is a radical design where, and you see one of my colleagues, Maria Sparopoulou, she's now on the faculty at Caltech. We are able to construct major pieces of the apparatus above ground, which was a tremendous advantage. We could commission those pieces, including all the instrumentation that measures particles beforehand, and then lower them down. And then what you just see there is the heaviest piece, which was 2,000 tons of a 12,000 ton detector, which was lowered in 11 hours to the ground, 170 meters below the ground.
Now this detects something, whatever comes out of a particle collision, right?
So there are different layers of the detector. What you mostly see are on the outside layers which detect the particles which are most penetrating, called muons, that get to the outside. Inside, what you don't see so well, after this was lowered to the ground, all the inner elements were put in that measure the particles emerging from the interaction region. What's interesting about this picture also is this, like many things what we do, is a technological feat. So this is by far the most ambitious magnet ever built. We use the magnetic field to bend charged particles to measure their momentum. And so this is a 40 kilogauss magnet, which means that that's about 100,000 times more than the Earth's magnetic field. It has a superconducting coil to provide the current that generates the field, and the stored energy is very large. It says something which is unfamiliar, 2.7 gigajoules. What does that mean? Well, that's the same energy as the kinetic energy of the largest man-made object, the aircraft carrier of the class, the Nimitz class, when it's moving at 20 miles an hour.
Okay.
So that's the equivalent energy stored in the magnetic field of this magnet. So this is, so what can we find? Apart from the Higgs, that's one of our first goals, we can see many things. And so here we've tried to catalog, are there more particles like the W and Z? Are there heavier partners of that? Is there supersymmetry? As I mentioned, supersymmetry has these dramatic signatures in which you not only see jets of particles, which is the same as we see in our standard interactions, but events in which there's a lot of missing energy. What does that mean? It means energy which escapes the detector through weakly interacting particles which have no charge. That's one of the signs of supersymmetry. What if there is no Higgs? We go to higher and higher energies, something goes wrong with the theory. When we reach an energy scale of about 1,000 times the equivalent energy of a proton mass, then the interactions become too strong unless there's new physics happening there. So we may suddenly find a new scale of new physics that says Higgless resonances at an energy of about 1 tera electron volt, which is again about
1 trillion electron
1
volts.
trillion electron volts, about 1,000 times the energy that's in the proton's mass. Then there could be new types of constituents of matter. This has a funny name, Technicolor. One of my friends works on this quite a lot. It's hard to make the theory work entirely, but maybe there are just new constituents of matter with new quantum numbers, just like the familiar matter, the particles have quantum numbers, you know, like charge. Maybe there are new quantum numbers. Okay.
All right, and
so what about extra dimensions of space? So this is what we described a little bit before. Imagine that in a larger subspace, we can only draw in 3 dimensions. So we'll represent the subspace as a plane in a bigger space. And so we're in this plane, and in the bigger space, gravity can travel, as shown here. And it's this ability to travel in a larger space that dilutes the force of gravity. Then also, you know, there's been a lot of discussion in the press about the ability to create black holes. First of all, the black holes we create, the microscopic black holes, are harmless. They evaporate in a very short time and emit lots of particles. And we don't think, well, it's only a speculation that we could create them in the first place. And if we do, they don't do any damage. We've actually searched for them, and we've already set limits on the mass of what they could be.
have we actually created any yet?
No, we just set limits. And these are other possibilities. Maybe we're separated from a higher energy scale by a sort of potential well, I mean a barrier. And well, we don't, so the bottom line is we don't know what's out there. We're going to discover something. We're going to discover the Higgs, which is the least exotic of all the possibilities, or we're going to discover something else. But we are going to discover something, because without discovering something, our knowledge, all that we know, doesn't hang together. And the greatest mystery would be not to discover anything. It means that we understand nothing, and we don't believe that.
Well, we've come a long way with what we do know. I mean,
Yeah.
we've done tremendous things with physics
tremendous
already.
predictive power. So then we can make a sort of transition to the practical aspects.
So you have 40,000 computers networked.
Well, yeah, I mean, actually, by now, the number of computing cores is more like 200,000. This is 40,000 computers.
And it's all over the world.
All over the world, and all the major networks. Actually, one of the things that I do as a sideline is I manage transatlantic networking for the field, because I was the first one to work on it in 1982. And so, but we cooperate with the major networks in the US for research and education. With Internet 2, we cooperate with the Energy Sciences Network, which serves the DOE laboratories in high energy physics. We cooperate with the Continental Network in Europe, which is called GÉANT, and many national research and education networks to run this system.
Okay, now let's look at applications of high energy physics and what this might mean to us as we sit here in Monrovia, and how this can affect our lives.
So this is an excellent question. You know, we've been talking about the future of our civilization, the very long view, how our civilization could be shaped over periods like decades to a century. And so it's natural for people to ask, what does it mean to me? What have you done for me lately? And the answer is, we are doing things all the time. One thing that I picked out in response to your question is applications of accelerators. So we use particle accelerators to generate high energy interactions, but different types of accelerators are used by the many thousands. There are an estimated 30,000 accelerators used for all kinds of applications, for medical treatment, for creating isotopes that are used in treatment, for diagnostics, for finding tumors, for material science, for industrial processes, for electronics, for biomedical research, and for understanding materials.
Can you show us the following displays, because I think you have actual itemized things here.
This is a sort of long list of all these things, things you can do to detect, to help diagnose or shrink a tumor, design a new drug, map a protein, make a better radial tire by partially curing the rubber. I'll get into some of this. Hardened surfaces, which means better ball bearings, better machine tools, better surgical cutting tools. Produce cleaner energy using particle beams to create fusion is a recent development. Spot suspicious cargo or luggage with particle beams, which are used in some airports to excite materials in the luggage which are symptomatic of explosives. Implant ions in semiconductors. Without that, semiconductors, most of them simply won't work. Prospect for oil. Clean up our drinking water. Reduce pollutants in flue gases. Reduce nuclear waste by transmuting long-term radioactive materials into shorter lifetime ones, so that
that would be very relevant, I think, because Professor Nate Lewis in our last program talked about the fact that we're going to need a tremendous amount of nuclear power. He said if we were to satisfy the energy required by the globe today, which is something like 10 trillion watts or maybe 15 trillion watts, he said you would have to build a nuclear power plant somewhere in the world every day for the next 40 years. So reducing nuclear waste appears to be, number one, extremely practical, because we're going to have nuclear power. He pointed out, I think in the last election campaign for president, one of the parties advocated 46 nuclear power plants. That's nothing. Yeah. We have to build one a day for the next 40 years?
Well, you know, I think it's true. Maybe it's a transitional period until we have solar power, but it'll be a few decades probably. There was an article today about a conjecture of how it could be done in 20 to 30 years, and that's at the short end. So yes, in the meantime, we have to deal with a lot of nuclear waste, and we need nuclear power plants. Okay, in the arts, detecting an art forgery or discover a hidden art treasure. People know about, you know, finding the masterpiece beneath the painting that the student painted over the masterpiece. dating an archaeological find, and then practical things like packaging a Thanksgiving turkey. So shrink wrap is done by treating plastics with particle beams.
Oh, so that's how it's done.
Yeah.
I wondered about that.
And of course,
one.
discover the nature of matter in the universe. I don't want to.
Oh yes.
Yeah. Okay.
Aside from packaging a turkey, okay.
So here I just put some examples of things. So the first thing that comes to mind is treating people medically. So there are about 10,000 cancer patients a day that are treated with particle beams.
Now this would happen then right down the road at City of Hope, very
Hope,
close to
yeah.
us.
Also, see here, Loma Linda Medical Center is a major installation, and they use ion beams. And the importance of using ion beams, also protons or heavier ions, is the ions travel a short distance. So by tuning the energy, you can tune where the particles slow down and then put most of their energy. So you can attack a tumor beneath the skin within your body, and deposit less energy in the environs around the tumor. And so that's the idea.
Mm-hmm.
And so that's done now quite often. And then also, these accelerators also create short-lived radioisotopes that are used for diagnostics. So for example, they give you, if you have some radioactive form of barium that you take, and then they look at where things concentrate to localize tumors. And there are 100 million such tests every year.
So I see you say generate $20 billion in business annually.
Yes, well, so, you know, medical treatments, and so this is big business.
Mm-hmm. Okay.
And of course, there are more things. This is hardly an accelerator. I mean, this has been around for nearly a century. To produce your dental or chest x-rays, I mean, you use a small electron accelerator. Interesting thing here, electron beams. Their use is much more than people realize. The largest use is to cross-link polymers. You have this long chain polymers, and if you expose them to ionizing radiation, some of the links are broken, and then they link up in different ways. And so you can change the properties of these polymers, like plastics. And so you create shrink wrap.
Shrink wrap, new types of woven materials as well?
Well, for example, there was something about tubing that protects wires under an automobile hood that's more heat resistant in case of tube. So when things heat up, so that they don't catch fire and things of that sort. Also, sometimes you can make polymers resist solvents, and which is useful, or be fire retardant.
Is Kevlar one of these that's treated by electron beams?
No, not that I know of.
Okay.
The fastest growing use is to cure inks, coatings, and adhesives. These are all over the place in everyday life. It especially eliminates the organic solvents. And this means that if you can cure them with a beam and not wait for a solvent or some curing chemicals, that you get much higher production rate, and you have far fewer chemicals with things, well, far fewer damaging solvents entering the environment. So that's very important. Also, I mentioned the cure rubber tires. You stabilize the matrix so that the tire cords can be held more firmly, and also gives a better balanced tire. And then things which are more obvious, like sterilizing food. And also you can disinfect grains and spices with them. Okay.
Or do you get objections from people who like organic food?
Well, let's say not lately, but the idea of sterilizing food to increase their shelf life with particle beams started around 1960. And I think because of the natural resistance that some people have to such things, whether they understand or not, I mean, it's become less universal than it would otherwise be.
Oh, I see.
Okay. So this is about materials properties. So semiconductors, as I said, need to be doped with an element which gives you either more electrons or more vacancies of electrons. That's what makes the semiconductors work. So by using particle beams to implant phosphorus or boron atoms in the silicon, it's extremely important for all our electronics. Then you can create integrated circuits this way. There are multi-step processes in which there's a role for particle beams to create devices. And I'm not sure if it's still true, but certainly in past years, the very smallest features were actually done by etching with particle beams. Implanting ions very precisely in metal surfaces, I mentioned, gives them greater hardness, so they're very good for cutting tools, and also good for medical prostheses, so that the metal doesn't corrode as much, and artificial hips and knees last longer.
Okay, very good.
This is about neutron generation. I found this very interesting. I mean, you challenged me about practical aspects. This is not something I do as my mainline profession. I came across this. I once invented a technique for calibrating some of our high-energy detectors, and it used a low-energy accelerator, which I investigated from various places. Ultimately, there was a company in Pleasanton that built one for us called the Radio Frequency Quadrupole. But I went to Berkeley, and I met some people there, and one person I met is a man who specialized in ion sources. And now, making this investigation, I see that he's created these very compact, very small, and efficient neutron sources. And creating such sources, which you do by you accelerate heavy water ions against other heavy water or against tritium, and you create a lot of neutrons. And there's here a small detector, only 8 millimeters diameter and 2 centimeters long. That's a neutron source, and a somewhat bigger one here. It's still not very long, but it's very intense. This has a lot of uses. The first use, the longest lasting one, is called oil well logging, is you put one of these sources down the well tube, and by irradiating the material on the edge of the tube, in the surroundings of the tube, you can measure the photons that you create, and there are some which are characteristic of organic compounds to search for oil. Landmine detection is a new thing that came up in the last few years. People want to detect mines with fewer false positives and to really identify the mines and also where they're located. And so by sending neutrons and seeing the photons come back or seeing low energy neutrons come back, you can see the characteristics of material in a mine.
Okay, let's move on to the next display.
This is an entire discipline that's arisen. How to understand complex protein structures in 3 dimensions. Not only to understand the structures, but also how they work. And so by using particle beams to create an intense flux of photons, you can then, in particular X-rays, you scatter the X-rays off the material, and from the pattern that's created, the diffraction pattern it's called, you can recreate the structures. And so there are many examples here. Here's one of studying HIV and how human antibodies manage to neutralize certain key parts so that the HIV can attack a cell.
So you're actually mapping organic structures,
mapping structures, and also doing it dynamically, taking sort of time snapshots and seeing the sequence of interaction of things.
Okay, let's see the next one.
And this is also a recent idea to use beams of ions to create fusion energy. So here you have a sketch of a scheme with 100 particle beams, and they're accelerated, and that flux of particles is used to compress matter, and as it gets compressed, the temperature rises and the particles fuse. It's like other schemes where you have a very high concentration of energy which creates a pressure front, and then you squeeze the matter, and then you're able to create nuclear fusion.
Oh, that's very important. All right, Harvey, I want to summarize a couple things here about your research at this point, and I wanted to show something to our viewers. This is an article that was published in Business Week magazine, September 13th, 1993. This was an article a long time ago, and it said, the super collider is science, the space station is pork. And this particular article was championing making sure that we would have a major accelerator here in the United States. We were building such an accelerator called the Superconducting Super Collider, circling the town of Waxahachie, Texas, which had an 87-kilometer ring, that's 54 miles, would have had 3 times the energy minimum of what the best that the LHC can do. So one of the things, you mentioned that the United States is not a major paying participant in CERN and the Large Hadron, and people believe, and I think Stephen Hawking said ideally he'd love to see an accelerator the size of the solar system. The bigger around you get, the more momentum you get, and therefore you can make discoveries better and more discoveries. So one of the things, the Super Collider was canceled in the early 90s. They had dug about 15 miles of this 54-mile tunnel. The article concluded here, and it said, America hasn't become so weak that it can't afford one big effort in basic science. And then you made a statement. To give up the major frontiers of science is to leave the field of world leadership. The energy frontier of fundamental physics is just such a frontier. Could you comment on that a little more?
Well, that is certainly what we believe. Our field has 3 major frontiers: the energy frontier, working at the highest energies, the intensity frontier, and the cosmic frontier. The energy frontier is where I believe we'll make the greatest discoveries, and this will shape our future knowledge and ultimately lead to more technologies, more applications, maybe in the long term. But what we are sure of, that in the long term, some decades from now or a century or even more from now, what our civilization looks like depends upon our fundamental knowledge of the universe and depends on research like this.
Okay, Harvey, I want to thank you very much for appearing on Science Solutions.
It's my pleasure.
Very educational, and wow, to actually cover nuclear physics as well as cosmology, and we've done this in our little program for us right here in Monrovia. Thanks again.
Oh, my pleasure.